what we have derived in the previous lecture is a matrix equation that can give us the coefficients, right? Now, we have a code that implements this matrix equation and gives us the coefficients. It seems very tight, right? It's just few lines, and all this is going to happen there. Okay, ready? Now, what do we give inside this function? We import f, the function, delta x, the order of the derivative, and the stencil. Okay? Then what's going on here? Can you tell me?
We are adding the nth powers of stencil to A.
We are adding nth power of stencils to A, meaning that if we, so this is going to be 0 anyways, right? These ones are going to be 0 anyways, so I can just remove these delta x's.
Can you remove the dot? I think you did something about
I think I did what?
I'm so sorry.
No, I'm explaining what we are doing. So I can also take this delta x squared over 2 factorial over to this side. So it's 2 factorial over delta x squared, right? Yeah. Okay. Then what I have here is basically, this is also 0th power of the stencil. So I have s1 to the 0, s2 to the 0, dot, 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 s1 squared, s2 squared, dot, 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 s1 cubed, s2 cubed, dot, dot, dot. Do you see it? So that's, it is constructing those rows with the stencil, right? Then create right-hand side vector. What do we have? All zeros, right? Only we have the factorial order. Where is delta x squared? Okay, I added delta x to the squared over here. Should I move it to the other side? I mean, I hope I will not break the code. If I break the code, I will fix it later. Can I think? It actually breaks the code because the coefficients will come out all ugly. So I'm putting this delta x squared at the end. Okay, I'm getting my coefficients. Then when it's time to take the derivative, I also implement this delta x squared. Good. What is this one? What is this one doing, this one?
Inverse matrix.
Inverse of this matrix over here times this one will give me the coefficients, right? Once I get the coefficients, now this is also a very interesting thing going on here. So what do you think is going on here? What is roll? You have to know what is roll, right? Okay, let me show you what is roll. I happen to have a code to show you what is roll. Let's add what is roll and what is its role in here. Anyways, so if I have 1, 2, 3, 4, 5, if you do MP roll U, comma 1, then it just rolls the whole thing to the right and puts the last one here. Okay? So if I do
cyclic permutation.
Cyclic permutation, very good. Or MATLAB version is circular shift. Circ shift, do you remember that? Maybe you do. Did you sign this new attendance? Can you please sign? Make sure that you sign the attendance. Do you see how it rolled like this? 4, 5, 1, 2, 3, 4, 1, 2, 3. Or you can roll to the other side and 3, 4, 5 and 1, 2. Okay, so what? So I'm creating this A that is composed of MP roll f minus I for I in stencil. So what is it is creating is, it's starting with a shifted value of the function by amount of stencil. If it's minus 2, it shifts to minus 2, right? Then minus 1, then 0, then plus 1, plus 2, right? Finally, it takes the dot product with coefficients and that shifted versions and sum them up, so you get your derivative as a function. Okay? Did you follow this? Okay. Okay.
What is flatten?
Flatten is very good question. What is flatten? Can you explain? Let me show you what is flatten. It's just some more like a Python quirk, right? So let me show you what is flatten. Let me get something. If I write shape, will it give me the shape? I hate when it doesn't work. It should be shape of U with MP. Yes. Okay. Basically, what flatten does is makes it a vector. Okay. It's like reshaping it, making it flat. So if you have a two-dimensional matrix, let me give you an example. Let's say D is equal to MP zeros 3 by 3 or 3 by 4 or random. So let me print D. Do you see? Yes. Now I will print D but flatten it. Then it just takes it into a string. It makes it a string. In this particular case, I used flatten because MP dot was not working. So I mean, if you take it out, somehow the shapes were not proper. So it would say like shape 3,1 and 300 not aligned, etc. Blah blah blah. So I would use flatten and it would work. Okay. So far so good. So let's see what I'm doing here. Order 1, stencil minus 1, 0, 1, and I'm trying to get first derivative because it's order 1 with this particular stencil, and this is my function, right? So then I'm plotting it and comparing it with analytical values, right? Okay. Do you see any difference? I actually did plot in blue and in orange the analytical values, but they are so good that they are underneath. Or the lines are so thick that you don't see them. So let's add some 0.1 here, 0.1 here, and you will see that they are right on top of each other. Are you happy? Yes? So this was the derivative of cosine. But it's not that good. It's just a matter of lines being too thick. Now let's do the error analysis of this. So I have a function, and it starts by defining the cosine and its analytical values. Then what it does is it calculates, if you write it as order 1, it calculates the first order error. Do you see how it calculates error? It basically subtracts one from the other, takes the square, and divides by the sum of the squares of the actual function. Okay? So what I do, let's say I take order 2 and I have a stencil of 3. So this means the stencil goes from, let me write as a note for you, minus 1, 0, 1. What is this one? Minus 2, blah, 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 right? So I'm increasing stencils, and I'm going to look at, let's say I'm going to look at the errors in the first order derivative. Are you with me?
Yeah.
Yes. What is this one doing? This one is sampling n from 10 to the 1 to 10 to the 3. Okay, and it's doing it in a log space in a linear way. Okay, so it goes from 10 to the 1 to 10 to the 3, but it's moving from 1 to 3 really. And we are getting the errors for each case. If you are ready, I'm going to plot it. Do you see? The error for 3-point stencil goes like this. So this is n. As you increase n, as you make it finer and finer grid, you get better and better precision. But let's say you are using 100 points. If you use, you have a question? No, okay. If you use 5 stencils, then you just jump from 10 to the minus 3 precision down to 10 to the minus 5. Do you see that?
Yeah.
5 stencil is this, 7 stencil is this, 9 stencil goes even further down, right? So increasing stencils is you are not paying too much price for that, right? It just goes linearly. You can use 3 stencil, then you have to multiply the function with 3 vectors. 5 is 5, 7 is 7, so it's very logical to increase the stencil. But after some point, it stops working. Do you see that? We will understand, sort of understand. We will pick at the reason by looking at Fourier transform. Yes?
Does it have anything to do with floating point arithmetic?
I think it has to do with, okay, I'm not sure. Maybe. I had 2 reasons. I haven't really reached at the ultimate reason. One reason was that. So are we taking enough integers after the decimal point? Okay. Are you following? Or it's just fundamentally you can't go beyond a certain point because of some Fourier stuff. Because I always thought, do you see, like, it's as if there is a line that comes here, a ghost line, that doesn't allow it to go beyond that line. And you can see that this hits that line here, this one hits that line here. You don't see it maybe, but green actually follows this line. Okay.
What about putting this up to 10 to the 7 or something like that to see if others hit that line?
Ah, yes, let's do that. Let's go. Do you see? The other one also hits that line. Very good.
And everything of that line, it almost looks like it's increasing.
This line, right?
Yeah.
Yeah.
And now I'm also calculating the slopes.
I didn't do it for the second order derivative, so let's do it for the second order derivative. Same story. Okay? All right. So let's talk about Fourier transform. Okay? So far, what did we do? We did finite difference. We used finite difference to find the derivative of a function. Now, we can do the same thing by doing Fourier transform, right? And in Fourier transform, you basically go from fx to another space where you have, it's just like going to the reciprocal space, right? Now, what happens, I hope you do know what happens to derivative of,
ik times f.
does everyone know this already? Yes or no? No? I wasn't prepared to explain this, but let me try. Do you know Fourier transform at all?
Yes.
I see. I see. Okay. Okay, so we have to start with Fourier transform. Now, first of all, the most important thing here is that, do you remember that if you start with a cosine, it would just slow down like that. Like if you take the second derivative, it just gives you cosine back, right? Now, what if you took cosine 2 pi over Lx? What would happen then? Let's plot it here. Do you see this function? It would look like that. Now the thing is that, so let me copy from here that function. Looks something like that. Now you can create, let's say you have a symmetric initial distribution. You can create any function by summing up these cosine terms. Do you agree with that? Etc. Assuming it's even. I'm trying to simplify stuff. Okay. So what happens is that if this is your initial condition, you can write your later stage condition just by simply writing e to the minus pi over L squared t e to the minus 2 pi over L squared t, right? So the solution of, let's say, heat equation basically then comes down to representing the initial condition as those coefficients, right? Now, how do you find those coefficients? If you multiply the other side by sum of the cosines, so if I multiply this side by cosine 2 pi over L x and integrate it, okay, on both sides, what will happen is that only this term will survive. Okay, the other terms will vanish. So that's how you find the coefficients. And once you go to Euler's formula, where it's like e to the I theta is cosine x plus I sine x, and learning more about this stuff, you realize that Fourier transform is basically integral e to the I kx fx over dx.
Should it be minus ikx?
Should it be? Yes.
It should be minus ikx.
E to the minus ikx. Very good. Okay. Did you follow this? This was like a quarter a semester thing taught in few minutes. If you don't follow, totally fine. Look at what happens here. If I take the derivative of this side, so how do we proceed here? Why the derivative is bringing the k?
Because we can integrate by parts. Also,
can I take the derivative of the right hand side? Okay. What would it bring me?
We can't do that. The left hand side does not depend x as a function. The formula is that the Fourier transform of the derivative is that solving at the prime value.
We have to do what?
So instead we need to calculate e to the minus ikx times f prime x dx.
Okay, let's do that. Then?
We can integrate by parts. and boundary terms vanish since we are taking it over an infinity interval.
Yes. And which will give us, okay, now I understand. Very good. Do you understand as well? No? Very good. Okay. So, Alper, right?
Yeah.
Alper helped me out with this. Thank you, Alper. So, this is u dv times type of an integral, okay? So, you can write it as u dv minus, u times v minus v du integral, right? And while doing that, you will bring, this term will give you, I guess, minus ik times a to the minus ikx, whatever. I mean, I'm not prepared to teach you this, so you get the idea, I guess. No? If you don't, I will prepare this next time for you. I'm surprised, to be honest, that you don't know Fourier series, so I'm sorry about that. But the point, what was the point? The point is that if you do this and you do the inverse transform, you get the derivative. That's how you get the derivative, by taking the Fourier transform first, multiplying it with k's, ik's, and doing the inverse Fourier transform. Ready? That's what I have. No? Just follow the code. Don't worry. Where is my code? Okay. This is the analytical part. So, what are we doing here? Fast Fourier transform. Okay? We are doing fast Fourier transform. Don't worry about it. Okay? So we get the Fourier transform. This is defining the case. And look at what we are doing here. We are doing df hat is 1i times k times f hat, right? So the derivative is inverse of that thing. Okay? And if we want to figure out the second derivative, then we do minus k squared times the f hat. Okay? Yes? You know what happens? It brings you very few complex terms because of accuracy stuff. But otherwise, it's actually, if everything was done properly, it has to return you, since you started with a real function, has to return you real function back when you do the inverse transform. It's about those coefficients, C1s, C2s, being perfectly symmetric. Okay? Okay, I've lost you, but consider this chapter to be a lost chapter. We will come back when we do quantum mechanics. Okay? Look, this also fits the analytical values. Do you see that?
This 0.1 difference is because we added them.
Yeah, we added them, by the way. Similarly. Now the error analysis.
Also, there's something very interesting about that.
Mm-hmm.
While taking derivative is a discrete operation, we can only take an integer number of derivatives. Taking the power, we can take it to n degree. So we can actually define the fractional derivative of a function defined that entire space using its Fourier transform.
Excellent. Does it go to the subject of fractional Fourier transform, or can we do it just by
just taking the Fourier transform times ik
to the n? Like I can do, what you are saying is that I can do this to the power of 1.3, and it would give me a fractional derivative.
Yeah.
Brilliant. Do you understand it? Let me explain you. What Alper is telling us is that, ik to the power of 1 gives you the first derivative. Ik to the power of 2 gives you second derivative. there is such a thing as 1.5 derivative. Like there are fractional derivatives that are used in where?
I think sometimes signal processing or optics use them,
Yes.
but I mostly encounter them in fractional Sobolev spaces.
Fractional what spaces?
Sobolev spaces.
Sobolev.
Partial differential equations.
Nice. I think you should be teaching this chapter. Okay. FFT error. Let's look at the FFT error. So same kind of story. We are doing the first order, second order, stencils and whatnot, and we are plotting them together. And we are encountering that line. It turns out that that line was the error that you get when you do FFT. So, are you happy? Yes? You can't go beyond FFT. I have started this exercise to see whether we can go beyond FFT. We can go better than FFT with increasing stencils. And I've been happily surprised that you can't. Okay?
Could you please increase the power of the 10? It seems like fast Fourier is slightly faster increasing downwards.
Okay.
There's also instability.
Yes, there's all sorts of instability here going on. Oops, I did the same thing, sorry. Yeah.
There's a very small gap.
Should be possible to explain with something. But otherwise, it's cutting it. Okay.
Also, how fast is fast Fourier transformation?
What do you mean?
I mean, how much time?
Okay. I was planning to also plot that, but I didn't. So let me not do it now. So let's go back to heat diffusion. Since you know Fourier transform very well now, this is the solution of heat diffusion using Fourier transform. So what we do is we just take the Fourier transform of the initial condition. Do you see that here?
Yeah.
Yes. Then we multiply it with, since we know that the derivative is k squared, we just simply multiply it with exponential minus the diffusion constant times k squared times t. We don't even go discretely, like delta t, delta t, delta t, delta t. We just can go straight, multiply every coefficient with e to the minus. Do you understand it? Yes. Was this like aha moment, or was it just you moving your head like this? Damn it, I thought it was an aha moment. Is anyone having an aha moment right now? Sorry. What? Okay. Okay. This is my bad. I prepared the whole thing by assuming that I would say like Fourier coefficient, and you would say yes, continue. Like, come to the point where you actually do the calculation. Okay, and that's why I failed. So this is the part where we do the calculation, and this is basically, if you run this, you start by this. And as time progresses, exactly what you expect is happening. So remember, it was a ring, and it's heat diffusion, right? So heat diffuses to the sides until it becomes flat everywhere. At least that makes sense, right? Yeah. Well, in Fourier transform, you can directly go with e to the exponential. But if you are using finite difference, then you actually have to resort to, again, back to the time evolution operator. Do you remember time evolution operator?
Yes.
Like -1, 2, 1, -1, a matrix, and you would took the exponential of the matrix. That's what we are doing here. So for this part, for example, we are using a 3-point stencil. At least today you learned stencils, right? Those derivatives. That's also a gain. Then we are doing this time evolution operation, and if we run this, it gives us similar result. Okay? The thing that I couldn't do, and I was worried that that would be the problem, is implement Fourier transform in a way that it implements boundary conditions. Okay? So instead, I implemented boundary conditions in the finite difference regime. So here's how I implemented them. Let me show you. This is again the matrix, right? So I wrote impose Dirichlet boundary conditions. Let me just change it to impose boundary conditions. Just what this means is that the matrix that is dealing with the edges are set to 0. So I'm not touching those parts, the boundary parts. Instead, I'm setting them, I'm leaving them alone, so I'm not changing them. One moment. Yes. I'm not changing them, and that way they stay the same. So that way I can solve a boundary condition where this time it's not a ring. It's not a ring. It's just fixed temperature. Okay? So I'm not changing. What?
It should converge to a linear.
It should converge to a linear thing. Yes. Very good. I mean, let's do it. Let's go to 1,000. I hope it works. Do you see that it converges to a line? Like you are keeping it at certain temperatures and it just falls and makes a line. We could also implement Newman boundary conditions, whereby you assume that there is no heat flux in. So how I implemented them is I just say that the very left one is equal to the next one. So it's starting flat. And the very last one is equal to the previous one, flat there as well. And let's run this. Oops. Do you see what happened? Okay, maybe we should take less time steps. So this time they are not fixed, but the derivative is going to 0 at the edges. So eventually the temperature would just go to the same point everywhere. Uniform distribution. Okay? All right. So we have 10 more minutes, actually 9 more minutes. I want to do damage control. So let me get some questions. Any questions? Yes.
This is the imposed boundary conditions. What is the difference between the periodic boundary conditions that we first assumed?
So the difference is that what is the difference between the periodic boundary conditions and imposed boundary conditions? The thing is that in periodic boundary conditions, especially the edges create no problem because you can just roll. Do you remember we were rolling? So when you roll, the last one comes over here. So there is always another point there to deal with, right? So you can increase stencil as much as you want, and you will always find a point to the left because it comes back to itself, right? But when you have actually boundary conditions that are not connected, then you actually have to put some thought how you deal with those boundary conditions. For example, if I have a function that goes like this, I can't really use Fourier transform because it's not a periodic function, Okay, can I?
It would give rise to edge, right?
Yes, especially at the edges. I mean, let me not say like it's impossible. I couldn't do it in like 1 week, but probably it's doable with some tricks. That's the point. Like, yes, what is the trick?
The Fourier transform is only valid either in line or torus. The space that we are taking Fourier transform over must have no boundaries.
So there you go. We have some troubles there, right?
Yeah.
So, did I answer your question? What is missing from my question, from my answer?
My background.
So, I mean, if you are considering 5 stencil, for example, 5-point stencil, then you will need to rethink what you do at this boundary, okay? Because you were using -2, -1, 0, 1, 2, right? Now you should actually use a different stencil, which is 0, 1, 2, 3, 4, right? So you should get your derivative, whichever order it is, by not doing central difference, but forward difference. And the good thing is that you have a general code. You can just put 0, 1, 2, 3, 4 in the stencil part, and it would spit out the coefficients that you need. Okay? Back to Fourier transform. If you have something like this, it's not periodic. Do you see? One way of dealing with this is to separate this problem into 2 problems. Okay? You know that what's going to happen eventually is a straight line. So you can call this steady state solution. Okay? And you can subtract it from the initial condition. If you are very lucky, you will end up with a periodic function. But that must be super arranged. Okay? And then you can say that I'm solving steady state separately and the rest separately. Then maybe you can use Fourier transform. Okay? All right. What other questions do we have?
Can we first define this u as cosine pi over x in number t? Did we assume that initial temperatures are just kind of cosine?
Yes, we did it for that particular case. So we
could choose some other.
yes, let's say this is something else, right? This is some function, x times cosine pi. It's just x, no. X times exponential x squared over 2, whatever. Okay? Then if you are doing Fourier transform, which you really can't in this case, let's say this is somehow periodic. Then you should have sine or cosine somewhere. Okay? Anyways, let's say it's periodic. Then you can write this function as the sum of cosines. Let me actually write it like this. X sum of cosines, right? Do you agree with this, first of all? Let's say this is also an even function, okay?
In this case, we can write it as sum of sines.
Okay. Let's say it's like this, or something that is even and can be written, okay? Now, the solution of heat equation is very easy. You just add this, n pi over L squared times T. Boom, you have the solution. The problem is finding these coefficients. And that's what you find actually with Fourier transform. That's why we could just get those Fourier coefficients and just simply multiply them with exponentials. But you can't do that in finite difference. Am I making sense? Other questions? Any questions at all?
Right now, we are solving the heat equation using Fourier series, which we can in bounded intervals, but we cannot take Fourier transform on bounded intervals.
Mm-hmm. So?
Sorry, only on unbounded intervals. Fourier transform is defined either
Okay.
on minus infinity,
So,
or circle.
I should really say discrete Fourier transform, right?
Correct.
I should be careful with my words. Fourier transform and discrete Fourier transform are two different things. Very good. Can I do this with Chebyshev polynomials?
We can do this using any family of orthogonal, any orthogonal family, but Chebyshev polynomials don't have that good under second derivatives, so it will be more complicated.
It will be more complicated, but can we go around the periodic boundary problem by using Chebyshev polynomials? What do you think?
No. I mean, for periodic boundary problem, we can take the Fourier transform only to, we can use the Fourier transform formula only for 0 to pi, and normally we can't use Fourier transform at bounded intervals because when taking derivatives we will get boundary terms with that integration by parts. But since circle has no physical boundary, we can actually do that. But we can only do it because of the periodicity conditions.
Okay. Okay. Is that a good point to stop? Thank you. Take care.